Welcome. We are looking at the thermodynamics of solutions now, and in the last class we got introduced to a property known as the excess property. We said that excess property, say MTE, plays the same role for solutions as the residual property MTR or MR played for the pure substance. And then towards the end of the class we said, let us look at one such excess property, such as the excess Gibbs free energy, and we are going to look at this with a very specific objective in mind. The focus here is to develop an estimate for the activity coefficient. Remember, the activity coefficient is the one that brings about the non-ideality of a liquid or a solid phase. Now, the total Gibbs free energy of a solution, and if you flip back to your second module, you will from equation 2.23a was GT equals sum over the product of Ni times mu I. We will get it from there, and let us call this equation 424. We will need to refer to this from time to time. So, we will give it a new equation number 424. So, GT is sum over Ni mu I. Now, if we substitute equation 4.8, which is mu I equals mu I hash plus RT ln gamma I xi. If you recall, this is the expression for a non-ideal solution of either liquids or solids, and if we substitute this into this equation 424, GT equals summation over Ni mu I, then we get GT is summation over, okay, before I do that I will tell you how this goes about. We are going to substitute mu I with mu I hash plus RT ln gamma I xi. RT ln gamma I xi could be written as RT ln gamma I plus RT ln xi. You know that ln of AB is ln of A plus ln of B. Therefore, if you multiply each term by Ni and sum it over all i's, we would get sum over Ni mu I hash, which corresponds to this term, plus RT times sum over Ni ln xi, which corresponds to this term. We will take that first. It will be actually sum over RT Ni ln xi. RT is common, so RT comes out, plus in similar fashion RT comes out here, sum over Ni ln gamma I. Let us call this equation 425. At the same time, the expression for an ideal solution we all know. If you look at this, mu I equals mu I hash plus RT ln gamma I xi. We know that gamma I brings in the non-ideality. So, the expression for an ideal equation, which is actually 4.6 that we presented earlier, would be mu I equals mu I hash plus RT ln xi. Right. Now, if we substitute this into 424, we would get GT ideal equals sum over Ni mu I hash plus RT sum over Ni ln xi. Now, you know where we are getting at. You know that the excess property is going to be the actual minus the ideal. So, the expression for the excess property in terms of mu I hash, gamma I xi and so on and so forth would be obtained if we subtract this equation, which is equation 426, from 425. As you can see, this term is going to cancel with this term is going to cancel with this term, and so only this term is going to remain for the excess Gibbs free energy. GTE equals RT sum over Ni ln gamma I. Let us call this equation 427. Now, if we assume constant temperature and pressure, the total differential, that is d of GTE would become, RT is common, the temperature is a constant, therefore you can take RT out, and then by chain rule it is sum over Ni d ln gamma I plus ln gamma I times dNi. first function into derivative of the second function plus second function into derivative of the first function. You do that for each, and therefore you need to sum it over all I terms. Let us call that equation 429. Now let us do an exercise. It is a very interesting exercise. It establishes one of the very useful relationships, but it is an involved derivation. It is involved at this stage, as an undergraduate stage. Therefore, what we are going to do to improve your learning, to get comfortable with what the various terms mean and so on and so forth, we are going to do this derivation together. Okay. Derivation is rather what is required is very simple. Start with the Gibbs-Duhem equation, which I will abbreviate as GDE, to show that sum over Ni d ln gamma I equals 0. How is it relevant here? Remember the previous equation. Here Ni d ln gamma I sum over, right. We are going to show that this term goes to 0. What I am going to do is start you out, then leave you alone for about 20 minutes or so to help you think about how to go about doing it, and then go step by step. We know that the Gibbs-Duhem equation, which was given as 223C in an earlier module, second module, was minus st dt plus vt dp plus sum over Ni d mu I equals 0. Just check the sign here, I think it is a negative. This is a simultaneous variation of temperature, pressure and the chemical potential, if you recall that special aspect about this equation. Now the first hint is to get to this from the Gibbs-Duhem equation. The first hint is consider the explicit functionality of the chemical potential as the chemical potential of the species I is a function of temperature, pressure and composition. Okay, this is the hint that I am going to leave you out with. For this special derivation, I am going to use a slightly different equation numbering scheme. I am going to use it something like this: 4.a1. Okay, all this a would correspond mostly to the details of the derivation. Okay, so this is the equation 4a1, and this is your hint. Starting with this, try to get at this, which is a long way away, but this is the starting point here. Let us see how far you get 20 minutes from now. Go ahead, please. Okay, hopefully you would have gotten to some stage, you would have started out with this and substituted it into equation 223 minus st dt plus vt dp plus this is sum over ni d mu I equals 0. If you need some more help, I will present a few more steps and then give you some time to work things out in a directed fashion. What we could do is, we say composition here, okay, this composition essentially is given in terms of either the number of moles or the mole fractions. Therefore, let us represent the composition through mole fractions here to begin with, and let us say that there are p components, okay, n1, n2 and so on till np. Therefore, you could write the Gibbs-Duhem equation as minus st dt, this we all know, plus vt dp minus ni times dou mu I dou t at constant p ni dt plus dou mu I dou p at constant t ni dp plus sum over all the, I mean this k is an index here, dou nk of mu I at constant Tp all other nj's dnk. The total number of components is p, this k is just used as an index for the sum of this term, this equals 0. Okay, this is the first term minus st dt plus vt dp minus sum of ni d mu I is written in by considering mu I as a function of temperature, pressure and the composition of all the species. Since you have p species here, n1, n2 represented by the mole numbers or this is actually the number of moles, it is not mole fractions, number of moles n1, n2, np and so on and so forth, you will have to sum over each one of them and that equals 0 here. Okay. And let us call this equation 4a2. Let me probably give you one more step or maybe a few more steps, here, yeah, this probably I should let you figure out. Now let us use the reciprocity relationships, okay, from the Gibbs-Duhem equation itself. Remember the reciprocity relationship, you could, if you have an exact differential and you write the expanded form of the total differential in terms of the partial differentials, then you could have a certain relationship between the various terms of the partial derivatives, the partial differentials, that is what we had seen earlier, and try to figure this out from this equation here or even the previous one, the compact GDE, dou mu I dou t at constant p n I equals minus dou st dou ni at constant Tp nj, which this is nothing but minus SIT hash, hash has somehow gone missing there, it is SIT hash there. This is the partial molar entropy, and this relationship is by applying the reciprocity relationship to the Gibbs-Duhem equation, and another reciprocity relationship would give us dou mu I by dou p at constant t ni equals dou vt dou ni at constant Tp nj, and this you all know what it is the partial molar volume of the species I. This is equation 4a4. What I would like you to do is use this and see what 4a2 becomes, okay, you will be very surprised. Use this, use these reciprocity relationships and see what 4a2 becomes, and I am going to give you some more time so that you will get into the feel of the whole thing. Let me give you about 10 minutes to do that. Go ahead please. Okay. Hopefully you would have realized that the partial molar volumes here, when multiplied by the number of moles, actually give you the total quantity, such as this. Okay, before that, let us also see that the mole fraction is the definition of mole fraction, it is the number of moles by the total number of moles. Okay, this is required to express the equation in a convenient form. We will call this equation 4a5, and by multiplying and dividing the last term, one of the things has gone missing, I think. Okay, it is coming next. Okay, by multiplying, and this is a few extra steps before we get to the point of use of interpreting the partial molar quantities by multiplying and dividing the last term on the left hand side of equation 4a2 by summation over Ni. This was the last term, sum over k dou mu I dou nk at constant Tp, all other n's remaining constant d and k. We are going to multiply and divide this by sum over Ni. Therefore, this would become d and k sum over Ni. Here you would have dou nk by sum over Ni. Therefore, this can be replaced by xk and this can also be replaced by xk, and therefore, the last term on the left hand side, the right hand side was 0, the last term on the left hand side can be reduced to sum over dou mu I dou xk at constant Tp. When these x's are considered, the x's would remain constant, the other x's would remain constants. So, Tp other x's remaining constant dxk. If we do this, if we write this in terms of mole fractions and substitute into 4a2, that would become minus St dt plus Vt dp. Now, this is where we are substituting the relationship from the that we obtained from the reciprocity relationship as operated on the Gibbs-Duhem equation. Remember, we got the partial molar entropy and the partial molar volume. So, the third term was minus of sum over Ni of minus Sit, this is what we got from reciprocity relationship dt, and the fourth term again from the other reciprocity relationship minus sum over Ni Vit hash dp minus we are writing this in terms of our compact mole fractions minus sum over I Ni, this was there earlier, this we have replaced in terms of sum over k dou mu I dou xk constant Tp all other xj's dxk, of course equals to 0. And from the definition of partial molar quantities, this is nothing but sum over Ni times minus Sit is nothing but the minus of the total entropy of the system itself. This minus St dt will remain here plus Vt dp will remain here, and there is a minus here, there is a minus here. So, this becomes plus, and we said that this is the total entropy of the system. So, St dt, this becomes minus by the same argument, this is nothing but Vt, the total molar volume of the system, total molar volume of the system Vt dp, and this term as the same minus sum over Ni times sum over dou mu I dou xk constant Tp xj dxj. Okay. Note that this is a double sum, which means for each of this term you need to sum over all the p terms and then take the next. For example, if you take n1, you need to run through x1 to xp, and then n2 run this to x1 to xp, and so on and so forth. That is the meaning of this. This equals 0. It is quite obvious that these terms are going to cancel. Minus St dt will cancel with plus St dt, plus Vt dp will cancel with minus Vt dp, and therefore, we have this of a nice form. Here minus is inconsequential anymore. We are left with sum over Ni summation of k dou mu I dou xk at constant Tp xj dxk equals 0. We will call this equation 4a6, and with division throughout by sum over Ni, in other words, we are going to divide the left hand side by sum over Ni and right hand side also by sum over Ni. Here it does not matter, we will get sum over I xi, Ni over sum over Ni is nothing but xi, definition of mole fraction, times sum over k dou mu I dou xk constant Tp xj dxk equals 0. Equation 4a7. Okay. I think we need to stop here, we are out of time. What we are going to do in the next class is substitute mu I in terms of mu I hash, gamma I, xi and so on, and see where we go. Remember, the whole idea is this is an exercise starting from the Gibbs-Duhem equation. We are going to show a specific relationship, that is why we are doing all this. Okay. See you in the next class.